Today I'll be talking about the power or scale of parameters efficient from tuning. Fine-tuning, model tuning is a de facto ways of leveraging large pre-trained language models for downstream tasks. However, the techniques require separate copies of model for each downstream task. To avoid storing multiple tune models, prompt design was proposed. Prompting depends instruction and few example to the task input and generate task output from pre-trained language model. In this example, the task is to identify the capital of England, and the prompt has an example of how to solve the task. Here, the example is identify Paris as capital of France. However, prompt design is still lost far behind model tunings due to the task description is error-prone and requires human involvement. Secondly, effectiveness is limited by how much conditioning text can fit into model's input. To address the issue of prompt design, Lee proposed prefix tuning. Prefix is subprompt or continuous task-specific vectors, which are prevent to all layers of pre-trained language model. The subprompts are trained using downstream task training data, while language model parameters are frozen. Prefix tuning addresses the issues of prompt design. However, it adds extra large number of parameters during training. So the goal of this paper is to propose a lightweight method of adapting large language model that is comparable to model tuning. In this section, we present a novel prompt tuning method. In this method, each task is represented by a k tunable tokens, which is prepared to input text. The tokens are called subprompt, which is trained on full label dataset. The entire pre-trained language model is frozen during prompt tuning. And in this paper, a frozen mask language model T5 is used. One design consideration is how to initiate prompt representations. The simplest way is to train from scratch using random initialization. More sophisticated option is to initialize each prompt token to each embedding drawn from the frozen model's vocabulary. In classification tasks, we can initialize the prompt with embeddings that enumerate output classes. Another design consideration is the length of the prompt. The shorter the prompt is, the fewer new parameters must be tuned. So we want to find the minimum length that the prompt tuning still perform well. Unlike auto-regressive language models like GPT-3, T5 is a pre-trained with reconstructing mask spans in the input text. The mask spans are mapped with unique sentinel tokens, such as from the text, thank you for inviting to your party last week. The mask input can be thank you X me to your party Y week. and the target output is X for inviting, Y less Z. Therefore, DeFi model never seen truly natural input text, not been asked to predict truly natural target. The author hypothesized that the original DeFi model is not a good fit for prompt tuning. So they explored three settings of DeFi models in prompt tuning. The first setting is spam corruption, which is in which the author used the pre-trained DeFi model of the self as frozen model. In the second setting, the author add the sentinel to the output of the pre-trained of the DeFi model. So they use the same model, but they prepare own downstream target with a sentinel to resemble the target in pre-training. And lastly, which is a language model adaptation, that the author adapted DeFi for additional steps to natural input and output, which transform the DeFi into model more similar to GPT-3. In this section, we present important experimental results and findings of the papers. Firstly, the author showed prompt tuning closed the gap with model tuning. In this figure, x-axis indicates the size of the frozen language model. Y-axis is super glue score. The higher score, the better. Green line is model tuning, and the orange line is a strong multitask model tuning baseline. The result shows that prompt tuning matches the baseline at 11 billion parameters, a frozen model, despite having 20,000 times fewer task-specific parameters. Blue line is prompt design, and the prompt tuning beats GPT-3 prompt design by a large margin. In this section, we present the contribution of each design decision on prompt length, prompt initialization, and pre-training objective. The first experiment shows the effect of prompt length. The authors changed prompt tuning for each model size while varying the prompt length in 1 token, 5, 20, 100, and 150 tokens. Blue line in the figure indicates single token prompt tuning. The results show that increasing length beyond single token is critical to achieve good performance. Notably, largest models still perform well with single token prompt. And across all models, increasing beyond 20 tokens yields marginal gains. The second experiment shows the effect of prompt initialization. The author trained models at all sizes while fixing other parameters. The green line is class-based initialization, which perform the best. There are large gaps between different initialization at smaller size model, but those differences disappear at larger size model. The third experiment showed the effect of spam corruption objective of DeFi model. The blue line is pre-trained use of the cell for prompt tuning. The result shows that the span corruption objective is not well suited for training frozen models to be later conditioned on prompt. Even adding Sentinel to downstream targets has little benefit. Orange light. However, the largest model gives strong result even with span corruption. Given that the language model adaptation shows bad result in previous experiment. The fourth experiment showed the effect of adaptation steps. Results show that longer adaptations provides additional gains up to 100,000 steps. This suggests that the transition from span corruption objective to language modeling objective is not trivial. And largest size model is robust to even non-ideal configurations. In this case, gains from adaptation are quite modest. By freezing the core language model parameters, prompt tuning prevents model from modifying its general understanding of language. Instead, prompt representation indirectly modulate the representation of input. This reduced the model ability to overfit to the dataset by memorizing specific lexical cues and spurious correlations. This suggests prompt tuning may improve robustness of domain shifts where distribution of inputs differs between training and evaluation. To prove this point, we explore two zero-shot domain transfer tests, the question answering test, and the paraphrase detection test. In the question answering test, model is trained on squad dataset and evaluated on other out-of-domain datasets. The table showed that prompt tuning outperforms model tuning on majority of out-of-domain dataset in terms of F1 metric. Specifically on textbook QA, the prompt tuning perform better than model tuning by 12.5 relative F1 metric. Next, we explore transfer between two paraphrases detection task. The QQP task asks if two questions are duplicates, while the MRPC task asks if two sentences are paraphrases. We test transfer in both directions, train on QQP and evaluate on MRPC and vice versa. First, training lightweight prompt tuning on QQP data and evaluating on MRPC gives much better performance than model tuning entire model. However, results are much closer in other direction, where prompt tuning show small improvement on accuracy and small drop in F1. As prompt tuning works in continuous embedding space, interpreting prompts is more difficult. To test interpretability of learned prompt, The author compute nearest neighbors to each prompt tokens from frozen models vocabulary. And they observe that for given learned prompt token, the top 5 nearest neighbor form tight semantic cluster. For example, they see similar clusters such as entirely, completely, totally, altogether, and 100%. This suggests that the prompts are in fact learning word-like representation. In conclusion, the prompt tuning is competitive techniques for adapting frozen pre-trained language model to downstream tasks. Its performance rivals that of the traditional model tuning, with gap vanishing as the model size increased. On zero-shot domain transfer, prompt tuning leads to improved generalization. Thanks for your attention.